Yes, perfect. Yes. So, okay, so as I said, thank you for listening. I will have a start outline introduction, why is our work useful, related to work, our methods, results, and conclusion of future work. Next slide, please. So, because this is more generic AI data science conference, our research area is natural language processing, having to do with understanding of pseudo-understanding of text and language, English and other languages. It's not necessarily the way people do it, but anyway, that's useful for a computer program to assist and help us. And there was a lot of recent progress with deep learning methods and large pre-trained model built by Google, Facebook, and other people who have access to large computing power and large amounts of data, even maybe everything that's text that's out there on the web in multiple languages. Even there are multiple language models called Multilingual BERT or GPT-3 for OpenAI and others. And why is this interesting? This deep learning revolution started with image processing. They finally got 10% or more improvement in image recognition objects. Then in speech recognition, that's why the voice assistants, Alexa, Google Assistant, Siri work better because they recognize speech. But they recognize the words. They don't recognize what we mean, the words and the meaning of sentences. So that's where we work with meaning of words and sentences in my area. Work with speech and text, but this presentation more about the text. So yeah, and it made the difference, this improvement of 5–10% or even more, it made a difference between commercial product versus just research prototype. And even the commercial products, maybe you know, they are not always very good. Sometimes they don't understand what you say in terms of speech, what words you use. But more often they don't understand what you mean, what the meaning of words and sentences. Next slide, please. So our paper is about word embeddings. So what do we mean by word embedding? How to represent the meaning of words. And it's a kind of distributed semantics, meaning it's a bit shallow, but the deep learning representations go a little bit deeper into semantics. Meaning, what do we want? A good word embedding, a good vector representation of words is one that groups similar words in the same space automatically, like all the colors, all the vegetables, all the animals. Ideally, even in multiple languages, so you can do multilingual models. And it's useful in classifying text, finding similar text like information retrieval. You type a query and retrieve documents, or even exact answers, like question answering, not just document retrieval. And classic form, TF-IDF vectors used in information retrieval, they are fast, but the vectors are very sparse. Like if you have 20,000 different words, the vectors will have 20,000 dimensions and lots of zeros, because not every word will be in every document. And they work good enough for information retrieval, but they retrieve wrong documents. The good thing is that we only care about the top. We don't go to read all the rest. But in text classification, you have to classify all the documents properly. So word vectors, word2vec, and other contextual embeddings, new types of representations, are much better in terms of performance. 10% better, a bit less or a bit more, depending on your application. And there are several kinds. Word2vec is we have several flavors that we improve in this paper. And the contextual embeddings are for each word in the different sentence will give you different vector. And this is more like our future to apply the method I will present today to them. Thank you. Next slide. So word2vec are available for download, and we can build your own, but it's better to use existing ones because they are pre-trained on very large data, and we don't necessarily have access to that large data unless we go and collect a lot. And the code is available, was produced by Thomas Nikolov, 2013. And the idea is not to count words, because counting words, it helps, because if you see that word with other words a lot of times, you kind of guess what the meaning of that word. So that's what these word vectors do. They don't explicitly model mean, but by a word that occur a lot with other words, kind of has similar meaning in the same, appears in similar context. Is the idea is distribution semantics. You know a word by the company it keeps. If you don't know it, you see many contexts, you learn what it means. But here it's not just counting, it's predicting. So you train some sort of neural network or other model to predict, if you see this context, what word would fit in there. It's a kind of language model approach. Next slide, please. And for example, if you see some word that appear a lot with apricot, what apricot is a fruit? What is that word? Maybe it's a kind of a food or dessert, or maybe it's a tree. So it depends on the context what the word that come near apricot will be. So and we don't necessarily want to classify, but we want to learn about every possible word, in what context, which words would fit better than others in a kind of text. And it's unsupervised in the sense that nobody needs to go label a lot of data like we always do in machine learning. It's called self-supervision. And the idea was by Joshua Bengio and later by Colobert for language. Self-supervision means you have a lot of text, take out some words, and then you try to predict what word would fit in there. And because you know what word was there, you have the label. Maybe other word will fit too, but you don't get points for that. Only if you get exactly the word that was there. It's called self-supervision. So its approach is unsupervised in theory because no labels in the data, but it learns the weight of the model in such a way to predict the right word back. And maybe by chance it will predict similar words, but then your algorithm doesn't give extra weight unless by the time you train all the models, it kind of starts with random vectors and improves them as it goes through the learning of. And this self-supervision is used a lot in computer vision too, in speech recognition, in language processing, maybe in others, because it's a nice way to do it. And in word-to-vec package, there are two vectors, skipgram and cbo, and you can use one of them. Skipgram kind of says, if you have a word, oh, sorry, please go back to the slide. If you have a word, what would be context in which it appears? Because you haven't seen that word in many contexts. In a new sentence, you give high score to sentences that predict the context in such a way that it makes sense on new data compared with what was in the training data. So starting with word, you kind of predict what fit in that context. And the other one is starting with the context, you try to see what word fit in the middle of that context. And you can use one of these two. Skipgrams work well when you have less training data and deals well with represents well rare words, versus the other one is faster to train, slightly better for frequent words, which probably make up the majority of your test data. And we will use one of them. There is two others. BLAV is not a neural network based, but is more like a very large corpus with some sort of weights and pairs, and encodes vector differences, which words appear in some similar contexts. What is the difference between vectors? It works well because it's trained maybe on larger data than word-to-vec. And the third one, next slide please, is fast-text embeddings, which are similar with word-to-vec, but they also have subwords. Instead of having, sometimes you have these large word-to-vec models, you download them, and in your test data there is some word that you don't have any vector for because it was not seen in the training data. No matter how large is your data, there'll still be some words that were not seen in there. Maybe it's different domain, maybe it's a name. So what fast-text does allows you subwords, maybe root or just n-grams characters. And if it doesn't know the embedding of a word and know the embedding of the parts of the word, it will aggregate one embedding for that. And you see improvement in performance if you use fast-text. So we'll use these three, word-to-vec, globe, and fast-text in our experiments. Then my student Zainab will take over, and hopefully we can hear you, Zainab.
Yes. Hi, everyone. Thank you, Dr. Diana, for the introduction. So I will start with the motivation for our work. So even though word embedding is remarkably effective in capturing meaningful regularity in both syntax and semantic, the assigning a meaning to the dimension of the word vector is still challenge. This presents a problem both generally and in a specific field. For example, in medicine, this will present a problem for sensitive fields such as medicine and law, for which the interpretability of result is essential to the technology widespread acceptance and adoption. It's also interpretability of word embedding can help us to deeper to provide us with deeper understanding of these embedding. It also could assist us with providing some solution to some problems that is already exist in the embedding space, such as a bias problem. So in this work, we introduced an effective and simple technique for interpreting word embedding dimensions. So also for the related work, several researchers also tries to tackle this problem. For example, Hanliski and Grovich try to introduce a framework for decomposing word embedding into smaller meaningful unit, which called sub-vectors. Zobnian employs several rotation algorithms to improve the interpretability of word embedding. Weishi proposed a joint non-negative sparse embedding with they use both text-based similarity.
Don't have sound up in the room. We try some more. Okay, now we can hear.
Okay, sorry. So they introduced text-based similarity and brain activity to improve the interpretability of word embedding. However, this technique is very challenging because it's needed great deals of time and efforts. And Farouqi's propose a transform word vector into sparse vectors. So they use the auto-sparse over complete autoencoder, and they transform the dense word vectors to the sparse word vector in a way to improve the interpretability of word embeddings. So in our method, we can describe our method in the following steps. So our method is based on post-processing techniques that we usually use to improve the quality, the overall quality of word embedding, and also to reduce the complexity of word embedding. So for our method, first we start with quantization steps or binary representation. So we convert the like the real value vector into binary representation using the sign function. So we map each positive value to 1 and each negative value to 0. After this step, we deploy a post-processing technique that is introduced in 2017 by Mu to further improve the quality of binary representation. And this post-processing technique, it was based on empirical assumption that word embedding shares a large mean, and by removing the mean of word embedding, we can improve the quality, the overall quality, and also we can improve some of the features in the embedding space, such as the isotropy in the embedding space. And the final steps to interpret the post-process word embedding, we deploy what's co-clustering technique to find the relationship between to find the relationship sub-matrices between a specific dimension and a specific meaning in a word. So this is basically our algorithms. So the input is the word vector, the word vector matrix A, and also for this to post-process the embedding, we need also the principal components. So initially, we can calculate the principal component using the principal component analysis, and this D represents the principal components. After that, we convert the word embedding into binary representation. We also apply some normalization step, and also we after that we apply the post-processing, and we remove the common or the top components. So in the original algorithm, they suggested to remove the first 7 components. And at the end, we get the post-processed word embeddings. So for experimental result, our main task was the co-clustering method, because we use the co-clustering method as an interpretability technique. And then we also did word similarity task and classification task to show that our method can produce also comparable result to the original word embedding in other NLP tasks. Co-clustering task. Co-clustering techniques are applied in order to order and organize data in a way to reveal the hidden structure. And there are several co-clustering algorithms that differs on how their they define the bi-cluster. Some algorithm cluster based on constant row or constant columns. Some of them they cluster based on high or low value. Some of them they consider the low variance or correlated rows and columns. So we select spectral co-clustering. This algorithm was developed in a way to cluster document and word simultaneously. The algorithm represents the data matrix as a bipartite graph, and it tries to find the best dense subgraphs. The two classes of these graph nodes represent the rows and the columns. In our case, we have the rows is the word and the column are the dimension, and the matrix entries specify the age in the graph. We deploy spectral co-clustering because it has the ability to identify specific dimension related to a specific semantic meaning. So the algorithm can assign each row, in our case word, and each column, in our case is the dimension, to exactly one cluster and seeks to arrange a subcluster in a diagonal structure. And we can see later the illustration. So for co-clustering task, we use two data sets. We use a PLIS data set. It has 200 words divided into 27 categories. And also the second data set is AB. It has 400 concepts across 21 categories. For purpose of our experiment, we combine some of these clusters because in the original data set, they are very fine grained. So we would like, for example, we have several types of animals. We combine these into one type animal. So in the original data set, we have water animal, bird, ground animal, insect, and amphibian. That's very hard to interpret because they have very semantic, very strong semantics. So we combine them into one cluster. Also, we did the same thing with planets and also with tools. And we ended up 5 clusters for each data set. So this is the illustration or the plots for the co-clustering techniques. This is for the AB data sets. So in the figure A, we have the AB data sets, and we plotted using the original GLOVE model. The X coordinate represent the dimension and the Y coordinate represent the number of words. And here we have the color map for the matrix entry. And if you can see in figure B, when we did the co-clustering with the original GLOVE model, it's very hard to detect the subclusters. In figure C and D, this is our proposed method. So we use the GLOVE binary BPA, our proposed technique, and we plot the AB dataset, and you can see there is difference in the representation of the data. Here in our method, there is more, the values is more distinguished. And when we tried and applied the co-clustering technique, we get this very distinctive subclusters, and we are able here to identify a specific semantic to the dimension and rearrange the dimension of word embedding based on the semantic relation with the specific words. So we ended with 5 subclusters, and they are arranged in a diagonal line. And we did the same experiment with the PLIS dataset. Also, in the figure A, you can see the original GLOVE, and after applying co-clustering, it's very hard to detect the subclusters, while in our technique in figure C and D, it's very clear, like there is a subcluster, and we can identify and give some semantic meaning to the dimension of word embeddings. This is here our the purity measure for the spectral co-clustering technique for AB and PLIS dataset. We use the three main word embedding: a glove model, a word-to-vec model, and fast text model. And we use our proposed techniques. So first, we use just the binary representation, and second, we use the binary representation with the post-processing technique. And we can see our proposed method outperform the original embedding models, especially with the glove model. And we can also observe there is a stability. We can observe some stability in the glove model, while in word-to-vec and fast text is not very stable. This is the result. We get the result after running the algorithm 10 times, and we select the best result. Here we have another task, which is the semantic similarity task. So we use the standard word similarity benchmark. This data set covers a wide range of domains, and we use it to evaluate our proposed method. Same thing, we use the three main word embeddings, and we can see in the glove model, our proposed method works very well. And also, we have some improvement in fast text and word embedding, but not like what we get in glove model. And finally, for classification result, also we used one of the very popular benchmark for classification tasks called CENT-eval. And we evaluate also our proposed model with the three main word embedding models. And also we get very good result with the glove embedding after we did the post-processing. So in conclusion, we introduced simple and effective post-processing techniques to enhance the interpretability, and also it also provide a comparable result with the original embeddings. It is cost effective because it's binary representation. So we can, this method, it could be used as a compression method to reduce the vector complexity and also storage need. We show our technique work well also with semantic similarity, concept categorization, co-clustering technique, and classification. Specifically, we recommend our method for count-based embedding models such as the glove model, because it shows stability and improve overall the overall the NLP tasks. And for the future work, we would consider a step forward to understand and interpret the dimension of word embedding model, and we aim to develop more models in the future. Thank you.